Hi everybody, welcome back to Chem 161. It's all Mega Man all the time this week. Let's see here. What do we have on the agenda? So, lab worksheet number 2 closes tonight. Make sure you get that in before the deadline. And then tomorrow is exam number 1. So, very important about the exam. If you have not requested to move your exam date, but you do want to move your exam to Saturday, you have to email me. If you email me today and I have not gotten back to you, I will do that after class. I just haven't had time to answer all the emails. But at 11:59 p.m., the request window is closed. You have to email me before Friday. Otherwise, I will email you back saying, please take the exam today. The deadline has passed. And then you will be expected to take the exam. And if you don't, bad things happen. So please be mindful of that. As far as content on the exam is concerned, we have one thing left to talk about, which is the Rydberg Equation. We're going to do that right now, after we talk about the Bohr model. And then once we get to the section marked quantum mechanics, so you are here on the slides right here. So the next few slides up to here are on the exam, but then starting from here, which we'll get to, will be exam 2 and onward. So. All right. We left off talking about a bunch of different crazy weird things that light can do, and a bunch of different crazy weird observations that we can make that light was part and parcel of. And it was until Niels Bohr that people thought, like, we know light is involved in this, we know the electrons are involved in this, like, we don't understand how. And what Niels Bohr did was he actually sat down and derived the equation for the Rydberg expression by hand, because there was no computer at the time for him to model his data for. So he just tried shit. And he actually stumbled upon something that worked. And you're going to see this formula and be like, holy crap, this is the formula you just guessed and tested? Like, yeah. All right. His proposal was that electrons live on specific energy levels around the nucleus, and that when you add light to an atom, the atom would absorb the energy from the photon of light by promoting the electron up to a higher level, and then when the electron decided to relax back down to the previous level it was at, or any other level really, the energy that would be released would correlate to the difference in the energies of those levels. And that's going to look kind of like this right here. So specifically, I have a bunch of levels. This is hydrogen, shown on the screen. Let's actually write that down. Where's my pen? There it is. So this specific diagram right here is for hydrogen. And in fact, the only atom we're going to consider in this class for this is hydrogen. In a later class, like Chem 1 or Chem 361, when you do quantum mechanics, you'll do this for any atom. But there is a very specific thing that arises that if we use an atom that isn't hydrogen, and that is that electrons repel each other, and you get a really complicated system that is impossible to solve. So, using hydrogen that only has one electron, we could simulate this very, very well. And what we observe is that for all these different levels, if we pick some n as our starting point, and then we fall back down to specifically n equals 2. The difference between 5 and 2 is enough energy to correlate to this wavelength of light. So if I type in E equals hc over lambda, and I put 434 in here for that, in nanometers, I will get this energy distance between these levels, 5 and 1. This distance would be between 4 and 1, or I'm sorry, 5 and 2, and then 4 and 2, and then this would be 3 and 2 for blue, green, and then red. Remember, red is lower in energy than purple, so it makes sense that the smaller drop between levels would correlate to the lower energy color. Now, this diagram is not to scale. A more to scale diagram would actually look like this. Oops, hold on. We'll come back to this in a second. It'll look more like this. So n equals 1 is very close to the nucleus. The nucleus is down here. N equals 2 is significantly farther away. N equals 3 is a little further away than that. 4 a little way further away than that, and then so on and so forth. And the distance between the two levels corresponds to, let me see if I can do this correctly, to the energy. Oh, I'm trying to write on the tablet, but I was looking at the tablet, and it didn't really quite work. Because I can't write sideways. Don't be ridiculous. So the energy between these two states. All right. I forget what was on the previous slide that I skipped over. Oh, right. Okay, so these colors correspond to the transitions that we observe. So this one right here, this red one, is specifically n equals 3 to n equals 2 in hydrogen, which you can see here. This is 5 to 2. This is 6 to 2. And then we have 7 to 2 and 8 to 2. Right there. And you can actually see that these lines bunch up towards the purple end, just like they do over here. So you could see that this structure is modeled in the spectrum. Now, what the heck is happening over here for helium and barium? Why do we get so many more different lines? And the answer to this is because what ends up happening is as we add protons and electrons to the atom, all of our energy levels change. Furthermore, we have more electrons, so there are more transitions possible because all the electrons are going all different ways, and they're all repelling each other. So we get splitting, we get different colors, we get different energy levels, we get different results. Now, another question for you is that if I go back here, you'll notice that there are only 3 colors, but how many different transitions could you do here? Well, I could do 5 to 4. Wrong end of the pen here. I could do 5 to 4. Where's 5 to 4 show up on here? And the answer is it shows up way over here in the IR region. So while there are infinitely many transitions possible, only these 3 show up in the visible region, although you can make an argument for 6 to 2, 7 to 2, 8 to 2. If your eyes are very, very good, you can actually perceive those purple lines. They are exaggerated on this diagram here. As far as I am concerned, when I look through the emission spectra, I can only see this one, and this one myself, and that these 2 are very difficult to perceive. And the reason for that is they extend into the UV region. And our eyes cannot see UV, but some people have better eyes, and they can actually see the faint purple that barely reaches into the visible spectrum. All right. The last thing to mention is that for these levels, these are discrete levels. Electrons move between n levels, but they are never in between them. And the reason for this is quantum mechanical in nature. Remember how we were talking about how electrons behave like waves? And that in order to observe the wave, you have to have a very specific amount of energy. If you don't have the correct amount of energy, you don't observe the wave. You just observe Garbo, right? Remember when the professor was trying to make the wave go up and down, and he got it for a bit, but then he had too much energy and it sort of collapsed? With electrons, electrons are going to settle in on that specific energy. If you give them too much, they will then just quickly go back to whatever the energy is for them to attain the wave that they are intending to. If you give them enough energy to promote them to the next wave, so n equals 2, n equals 3, etc., they will settle into that one until they release that energy in the form of a photon, falling back down to the previous level n. The takeaway here is that my electron can never be at like n equals 2.8 or something like that, and thus I only ever get these fixed colors when I look at the spectra of these elements. And again, since there are infinite transitions, but we only see a certain number of ones in the visible region, the other transitions must fall outside of the visible region, either in the UV region or the IR region. So for instance, going back to this diagram one more time, anything that falls to 2 is in the visible region, and that's purely by circumstance. But things that fall down to 1, so this right here, this would be UV because the energy is too big for us to see, whereas 5 to 3 would be IR. And then anything to 2 happens to be visible. And we just write that down here. This is more of a curiosity in this case right here. And again, it's the energy distance that the electrons are falling that counts for the energy that tells us where it will end up on the spectrum. All right. We're going to call this number over here. We're going to give it a name now. So instead of just saying n, what this is the principal quantum number. In other words, it's the principal number that dictates the amount of energy that the electron wave function has. The lowest level n is 1. That corresponds to, again, remember when we were talking about waves in that video, the first harmonic, or the first wave function. And then we can go to n equals 2, n equals 3, n equals 4, and we do this all the way up to n equals infinity, where you have an infinite number of wavelengths within this little, within this dimensional shape that we're just describing. I don't want to get too into detail here. I'm stepping into 361 territory. I almost said one-dimensional box, and you probably would have all been like, what the hell is that? And that's just a model. You can imagine this diagram right here as being a one-dimensional model where my electrons only go up or down. Like, there's no left or right. There's no depth to it. The electrons can only get closer to the nucleus or further away. And that's sort of where we're going with the 1D box. Now, remember that for every time we increase the number, the principal quantum number, n, we start introducing things like nodes, right? We're going to get to that in a little bit. Now, in terms of size of where the electrons can be when they're n equals 1, n equals 2, n equals 3, etc., the energy also correlates to the distance that they are away from the atom. So if I move an electron from n equals 1 to n equals 2, I'm actually physically taking it further away from the atom. It has a higher potential energy because it is further away from the nucleus. In the same manner where if something has a higher potential energy because I lift it up higher off of the ground, it will have more energy when I let it go, right? It's the same sort of principle. All right. Now here is the equation. This is the Rydberg equation that Niels Bohr figured out by hand. Like, holy shit, dude. How did he do this? I mean, that's why he has a PhD and is in the history books. Whereas I look at this and I immediately give up. And so the Rydberg equation says that the inverse wavelength is going to be equal to some constant that is specific to hydrogen divided by the inverse square of the different energy levels. Sorry, multiplied by the inverse square of the difference. I don't know how to say it. Just you can see it on the screen here. There's too many mathematical functions nested in each other, and I'm just like, huh? I don't know how to words this. There's the formula, though. Now, you'll notice that N1 and N2 are not labeled final minus initial, and the reason for that is it's going to depend on what outcome you want for the problem. Wavelength always has to be a positive number. So you cannot have a negative wavelength, right? And the principal quantum numbers always have to be an integer value. And then R is the Rydberg constant. That's just equal to this. 1096776 times 10 to the 7 per meter. Now, because we're looking at 1 over lambda, and I could substitute that into this expression, right? This right here is this part right here. I could get the energy of any transition by just saying this expression equals hc times all of this stuff, right? Because this is all 1 over lambda. So that is something that we're going to do in a later lab. I forget which lab that is. I want to say that it's number 3. It might be number 4. But that's going to be a lab that we actually have some class time to talk about. Or I will give you a video that demonstrates what you're supposed to do for that. Because we'll show how energy is useful for the Rydberg equation. But the most important part of this equation is to remember that lambda has to be a positive number. And the reason for that part being important is because this right here is negative. If I put in an integer for these right here, so for example, if I say n equals 1, or I'm sorry, n sub 1 equals 1, and n sub 2 equals 2, then what I end up getting in these parentheses would be 1 over 1 squared, so that's 1, minus 1 over 2 squared, which is 4, which equals this, right? 1 minus 1/4 is 3/4, or 0.75. But what happens if I reverse the numbers? If I reverse the numbers, now I get 1/4 minus 1, which would be negative 3/4, or negative 0.75. So if I flip these numbers around, I flip the sign on this. And then I multiply by it all, and I would get a negative wavelength, which is impossible. But could a negative energy be possible? It could if I was looking for the difference in energy, so I could get a delta E. So the equation, generally speaking, is used in such a manner that it will calculate wavelength, but because it can also be used for energy and energy differences, and you could say, oh, what's delta E for the atom? Well, the atom lost energy in spitting out a photon, so you'd get a negative delta E as a result. So you could get a negative number if you needed it for that purpose, but generally speaking, you don't want a negative number, and so what you're going to want to do for that is, I don't know why I'm erasing it this way, because I'm just going to write over it here. So when you do this part, put the larger n value for n1. That way you will get a positive output in the parentheses. I'm sorry, that's totally wrong. I sat there thinking about, like, which number do I want? And I just completely bumblefucked the answer here. N2 should be the larger n value, because then this becomes a smaller fraction that you're subtracting from a larger one. So I apologize. I don't know how to maths. It's because I don't trust maths. That's all. All right. Let's look at an example of this in action. This is basically what I just talked about, so let's look at this in action. I want to look at the wavelength emitted from the transition for an electron falling from 3 to 2. So let's do that. All right, so first I'll write out the Rydberg equation. So I'm going to say that this is 2, and this is 3. So that way I will get a positive number. And then the Rydberg equation, the Rydberg constant. I don't remember the Rydberg constant, so I got to look that up. It's like 1096776 or something. For some reason, this isn't helping me. Oh my goodness, hold on. PowerPoint's being stupid. 1096776 times 10 to the 7. One, two, three, four, 5. Did I forget a number? Hold on. 1096776. Okay. And this is per meter. So 1 over lambda would be that times 1 over 2 squared minus 1 over 3 squared. And so that's going to give us the inverse wavelength. So we'll go like that. 1096776 times 10 to the 7 times parentheses. Here's what I'm going to do this. So I'm going to do 2 squared, which is 4, and I'm going to hit this button right here, inverse. 1 divided by that. Boop. So there's 1 divided by 4 minus 3 squared is 9, inverse. I'm going to close the parentheses. So that's the difference between those two, times the Rydberg constant. And that's what I get. One, two, three, four, five, 6. Now, because these are integers, these are exact numbers. And then this is 7 sig figs, I believe, yeah. So my answer should also have 7 sig figs. Now, to get this, in order to get lambda out of this, I would just take my answer and invert it. So this number that's shown on the screen, I'm going to just hit this button again. Boop, there you go. And you get 656 point... I shouldn't write it that way, actually. I get 6.564695 times 10 to the minus 7 meters, which when I change this to nanometers, I get this. And when I compare that to the visible spectrum, we see that, oh, yeah, that falls in the red region, which is why we observe a red light for this transition. An electron falling from n equals 3 to n equals 2 in hydrogen will produce a red photon that you will see very easily. because it's smack dab in the middle of the visible region. All right. And then what color would this be? Well, we just said it would be this color, red. All right, you've seen me do that. And there's our summary. So we already said that this works only for hydrogen, yada, yada, yada. There we go. That's what I want you to do. I want you to do 4 to 2 for me, and I want you to tell me, A, what is the wavelength for the 4 to 2 transition? And then B, what color is that on this spectrum? So you've already seen the red line that's 3 to 2. Probably something obvious thing. The next one's 4 to 2. Yeah, it is. But tell me what the wavelength is that you calculate using the Rydberg equation. I'm going to give you 4 or 5 minutes to do that, and then we'll go over the results in just a second. 1 more minute, we'll go over the answers. All right. So let me get this screen up here real quick. All right, so we've got 1 over lambda equals Rydberg constant minus this quantity. And so 1 over lambda is going to be equal to the Rydberg constant times 1 over 2 squared minus 1 over 4 squared. So 1 over lambda would equal 1.09676 times 10 to the 7 times... So this would be 4 to the negative 1, or negative 2, about 4 to the negative 1, minus 16 inverted, boop, boop. So there's my 1 over lambda is 2056455 per meter. We're going to invert that by hitting this button right here. Boop. Lambda becomes 4.86273 times 10 to the minus 7 meters, which equals 486.2737 nanometers. And what color is that? Well, you can tell from the line there that that corresponds to cyan, which is this line right here. Because of course it is. Hopefully that's what you meant by blue, because this other one over here looks almost blue to me. All right, and that's everything you need to know for the exam. So, could I go back 1 slide? Sure. Or do you mean go back to the PowerPoint, or not PowerPoint, the Photoshop? The whiteboard, okay. Yeah, that's what I thought. Oops, that doesn't actually get you there. That's what I need to do. There you go. Yep. All right. So that's the Rydberg equation, and that's the Bohr model. So the electronic structure of the atom can be observed using the Rydberg equation. And then from here on, what we're going to do is we're going to use that model to basically explain everything else. Now, something very interesting is about to happen here. And I don't mean in terms of quantum mechanics. What I mean is, here is what that interesting thing is going to be. We're going to cover up the calculator. because we're not going to use the calculator again for the remainder of this quarter. So that's why I wanted to do that part for the exam, because that is all the math of Chem 161. Everything past this point, you do not need a calculator for. So we're going to trash it. We no longer need the calculator. So when we come back from our break here, which we're going to take right now, no more math, which for some of you, that's a really scary thing, isn't it? So we'll take a 10-minute break, and we'll play more Mega Man music, and we will contemplate just what exactly we have gotten ourselves into, because there is no more math in this class. Alright, we're back. No more math. No more math. Now, I do have the calculator hiding over here that I could just kind of go, boop. Oh, wait, I gotta do that again. So I go, I'm not clicked on the right thing. I could just go, boop, 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 boop. I could just reveal it if we ever need it temporarily. But as far as I am aware, we're going to refer to some formulas and we're never going to actually use them. We're going to refer to one very important formula and then never actually use it, other than conceptually. So we won't really need the calculator for that. But yeah, for the remainder of the quarter, everything we talk about here is conceptual. So we're going to be learning how to do electron configurations. We're going to apply that to bonding. We're going to apply that to orbitals to get more complex bonding. And then that's the end of the quarter. So I got to put the chat on here that so I can see it. All right. So again, from this point forward, not exam 1. This is all exam 2 stuff. So you'll be tested on quantum theory in week 10, which means you should know it now and you should know it later. But I'm not going to test you on this stuff specifically tomorrow. All right. Let's go ahead and get started on this. All right. Now, any object that you manipulate around you follows what we call classical mechanics. So this is basically Newton's stuff. If you throw an object, you can model its trajectory very accurately. If you push an object, you know how much energy it will take to do that because you know its mass, you know how much friction there is, you know how much elevation you have to lift it across, etc. So work, energy, force, etc., all that stuff follows classical laws of mechanics. Things that are atomic size do not follow classical mechanics. They are too tiny. and there are too many other odd forces at play. They follow what's called quantum mechanics. And what this means is that, in other words, they behave like waves. Things that behave like waves don't follow classical mechanics. Like, I cannot throw a baseball at a catcher and then say, oh, there was its wavelength. You can see it. Even though baseballs do actually have a wavelength. Everything has a wavelength, it turns out. But as we're going to see in some of these examples that we're not going to calculate because I don't care about de Broglie wavelength, we're going to learn that the wavelength is so tiny that it's impossible to observe. Let's talk a little bit more about what waves can do, though, mathematically. If I take two waves and I have their phases line up correctly, they will sum together, and I will get a stronger wave as a result. So here I have all my peaks, which I'm highlighting in red here. These are all lined up more or less exactly. And when I line peaks up with peaks, I get taller peaks. So there are my tall peaks here. This is called constructive interference. All the tops of the peaks will line up. They will all sum together. However, if I do this, where I have my peaks and my valleys line up, and they're offset like this, then what ends up happening is that when I sum them together, I get 0, because I'm adding a positive result to a negative result, right? This is called destructive interference. Destructive interference will neutralize the effects of a wave. Now, we can actually observe this in action. I think I have a link here. Yeah, I do in a second, so we'll get to that. So this is going to depend on how offset the two waves are. Here, there is no offset. My waves line up exactly. So at time equals 0, I'm at a peak on both waves. But over here at time equals 0, I'm at a valley on one wave and a peak on another. So my waves are offset by this much. Lambda over 2. That's exactly what noise canceling is. Very good. Yeah, so a noise canceling pair of headphones, what they attempt to do is that any incoming sound waves from outside, the inverse of, or the, not the inverse, but the offset of the wave is attempted to be played. And so the sound cancels out and you don't hear it. Oh, sorry, I had to yawn now. Now, another feature of waves is that if a wave strikes a wall, it will bounce off. But if the wave strikes an opening in a wall and tries to pass through it, what it ends up doing is it ends up bending around the corners, like this. This phenomenon is responsible for why I can stand around a corner, shout, and you would actually still hear me. Because my voice, which is propagating as a sound wave, isn't going to go in a straight line so that it never reaches your ears. It will bend and diffract as it goes around the corner, and you will hear some of the sound. Now, most likely, the sound that you will probably hear will be my voice reflecting off of other walls to get to you. But there is some of this diffraction that occurs for sound waves. We can actually see this in action here. Oops, sorry, I thought there was a second text there. Let me click on this video here. And we'll put this on the screen. So this is just a video that I found that diffracts waves in a water tank. So what we're going to do here is you're going to see... So what this is a tank of water with a piece of, like, white... I want to say it's like white paper on the underside of a sheet of glass that the water is in. And what we're doing is on this side over here, we have like a beam that we're just going up and down and up and down. And we're just stamping it in the water to create a wave. And what ends up happening is that if I pass my wave into a wall, it'll just bounce off. And you can see it kind of bouncing off over here where it's getting complicated. I want to go back a little bit. But here my wave is passing through an opening. Here's a wide opening, and you can see that the wave more or less goes straight through, but it's kind of curving at the sides here. If I make the opening much more narrow, then you definitely see that it diffracts and curves around. Now, interesting things happen if I have multiple of these. And what ends up happening is that these diffraction patterns overlap, and where they overlap, we get interesting results when it strikes the end of this wall. You're going to get a result that looks like a dotted line that will correspond to peaks and troughs. Now, this phenomenon still happens if we have a curved wave to begin with. And you can see this even if there isn't a slit, even if there's just a corner going around. These will eventually converge back to each other. And you have seen that in things like, say, water. If you have like a rock in a stream, the water, even if the water's choppy like a wave, it doesn't just be choppy and then the middle is perfectly still. It'll eventually converge back together. Oh, I have this on the wrong monitor because I was watching the video, so I gotta move this back over. Okay. So let's go back to that experiment where we had two slits here. A phenomenon that occurs is that if I have a wave that goes through two different slits, my wave will diffract on both sides. And then what will happen is that these waves will interfere with each other. And they'll interfere at different points depending on where my wave is propagating from. So this blue path right here, this wave, oh goodness, PowerPoint, why? My wave will interfere on the blue line with the other wave where they interact at this point on this wall. Whereas this red line right here, my waves will interfere in a different manner. It's the same wave coming along here, but it will be at a different point. This one will have traveled slightly further than this one, so they'll be offset in a different sort of way. You can see that the blue line here, my waves have traveled the same distance. So this will be constructive. And thus, where I hit the wall, when those two waves interfere, I will have a maximum, and the wall will detect that. Now, if I offset it so that this path is longer than this one by lambda over 2, I will get destructive interference, and I will get a 0 as a result. It will cancel out. Now, here we're using light. Light behaves like a wave, and then I'm going to observe the effect using photographic film. And the result is that I get this pattern. I get this pattern of constructive interference, destructive interference, constructive interference, destructive interference, over and over and over, and it looks like this. This is called a diffraction pattern. And really, what this diffraction pattern is telling us is that this is a wave. If you pass something through a double slit sort of situation, and you observe a diffraction pattern, then what you pass through those slits is a wave. And so this will work with anything that is wave-like, that we can also then impress upon this film. So light is a good candidate because the more light that strikes part of the film, the darker it will get, or the brighter it'll get, or whatever, however it is. But you'll see the pattern when you develop the film. With waves, you'd have to measure like height or something against like a wall, and you could still do it. Okay, well, if waves do this, let's try the next obvious thing to test. Let's try this with electrons. What happens when I do this with electrons? Well, here's what we would predict. We would predict that if electrons behaved like waves, they would cause a diffraction pattern. But if electrons behave like particles, particles would just hit the wall and rebound off of it, but then pass straight through without any diffraction on the sides. So we now have a methodology by which we can test, is something a particle or is something a wave? And so we're going to try this with electrons. Here's what we expect to happen on the left. And we did this experiment in the 1920s. This is what you would expect to happen. Your particles are beamed through these two slits. Only the spaces where the slit is should hit the detector. And so you should get two white lines indicating two bright spots for your particles that are beamed through the double slit. Here's what actually happens. You fire the electrons through, and you get an interference pattern. So electrons, even if you only fire one electron through, this is the weird thing. You put one single electron through, you still get an interference pattern. So this is not like, I could fire one electron at a time and see what happens. No, if you do only one electron, you still get an interference pattern. Now, the consequence of this is that this is evidence that matter, because electrons are matter, has a wave-like property to it. And so that can be modeled by this equation here. We're not going to actually do any math in this equation. I'm going to show you some math, but I just can't be bothered. The problem with this equation is that v is velocity. This is not frequency. And I've fucked up my Greek here. Hold on. So this is not new. Now you've seen why I've been drawing these like curly V's for new. And it's because there's a formula with V in it, that's frequency. We're going to work with this formula conceptually, and that's really it. The wavelength of an object is simply Planck's constant divided by its momentum. Momentum is mass times velocity. Now, Planck's constant is a really, really small number. So dividing anything by a really small... Dividing a small number by anything is going to make a ridiculously small number, unless you have a tiny, tiny object going incredibly slow, I guess? Yeah. So there's our formula. If lambda is the wavelength and v is the velocity and m is its mass, they are related using the Planck's constant. Now, in case you wanted to know what the joule was, that's the definition of it down there. A joule is 1 Newton meter or 1 kilogram meter per second squared. Because mass will be in kilograms, velocity will be in meters per second. We want our units to all cancel out so that we get something in meters for wavelength. But here are two examples. So if I have an electron moving at, say, like 0.01% of the speed of light, here would be its calculated wavelength. So if I used lambda equals h over mv, and I looked up the mass of an electron, and then I imported this velocity, this is what I'd get. Now, interestingly enough, this would be in the X-ray region. If this was light. The wavelength of an electron moving at this speed would be about 27, or would it be 27? No, it'd be 0.27 nanometers. So we'd be in the X-ray region / gamma ray region. But this is remarkably close to the X-ray region or the visible region or the UV region, right? So you might have heard of something called a diffracting or scanning tunneling microscope, electron microscope. We can use electrons to behave as light because they behave like waves. They will diffract, they will interfere, and they will create patterns on film, which we can then detect and print out as a picture. So we can use electrons because they have a similar wavelength to light. So that is an application that we can apply this concept of small particles having waves and not having to rely on light. Now, as an example, for the opposite side of this equation, if I had a very, very heavy object relative to an electron, say a baseball, and I threw it at a typical speed, which is not very fast, the wavelength for this, when you calculate it, would be this teeny, 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 tiny number that you would never, ever possibly observe. You cannot see something 10 to the minus 34 meters long. So the point of this discussion is that in order for this equation to produce numbers for wavelength that are observable, our objects have to be very, 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 very tiny. And if our objects are small enough, they will have wavelengths that are on par with other things that we can observe, such as, say, light. That means that we can use them for those applications too. All right. Here's the last quantum oddity that we're going to talk about before we go on to a more structured discussion about electronic structure. This experiment that we're doing here, the laser that is placed here is going to be set up in such a way that when the electrons pass through the laser will let us know, hey, which slit did the electron pass through? So if we fire one electron through the double slit, we should be able to hit the laser. And if we observe that the laser said, oh, okay, the electron came through the first slit, then it's behaving like a particle. And if it has a diffraction pattern when it does that, we will have evidence that we have observed both a particle and a wave, which would tell us that the wave-particle duality of light and matter is solvable. But it turns out that when we do this, this is the pattern that we get. So if I set up a laser to interfere with my electron to tell me which slot it's coming through, then the data result that I get also reflects that. So this over here, oops, where's my cursor? There it is. So this over here matches what the laser experiment is doing for us. In other words, we can't entrap the electron to show us wave properties and particle properties at the same time. Because we're actually doing a functionally different experiment. We don't see the diffraction of the electron because we aren't diffracting it anymore. We're sending it through a diffraction grating, and then it hits the laser, and then now it is no longer going through a diffraction grating. It is simply just an electron that has been ricocheted or rebounded off of the laser. Why would it suddenly lose its wave-like properties? Well, we have bestowed it different properties because the laser has struck it. And this is what leads to probably the most misunderstood concept in quantum mechanics, which is known as the uncertainty principle. The uncertainty principle, a lot of people think, involves Schrodinger's cat and like a radioactive sample. And in reality, what is actually happening here with the uncertainty principle is actually quite simple. I am taking a very tiny object, incredibly tiny. So here's my object. It's this little tiny thing. And how I am going to observe it is by colliding this block into it. And then after the experiment has happened, the block says, oh, I found it. It was right here. But where's my object? Well, now the object is anywhere. I don't know where it is. So the analogy that I use for this to explain the uncertainty principle is, imagine that you were trying to detect bowling pins. And the way that you are going to use your senses to detect them is that you're going to throw marbles at them. Now, you can't use your eyes because your eyes are unavailable for, I don't know, whatever reason. It's dark or something. So you have bowling pins in a dark room and you're going to throw marbles at them. If you hit the bowling pin, you will know, oh, okay, I found it. There's the bowling pin. And you could throw another marble at it and you'd probably still hit it again, right? So that's a terrible representation of a bowling pin. So here's my bowling pin, and if I throw a marble at it, the marble will bounce off, and the sound will tell us, oh, I found it. It's right here. And you could keep throwing marbles at this because the marbles are really, really tiny compared to the bowling pin. Now let's do another experiment. I'm going to use a bowling ball to detect my bowling pins. And what does the bowling ball do when it hits the pins? Well, the pins go flying off, and it makes a really satisfying sound, right? So you learn, I found it, but it's really no longer there, right? Because it has been launched off. When you do the experiment, you gain information, but you completely destroy the state of that information in this case. So if I threw a second bowling ball at this, what I would learn is, so if this is where my bowling ball was, and I throw my bowling pin, I throw the bowling ball at it, I would learn, oh, it's not there. And so in the laser experiment that's going on in this right here, the first experiment is the laser hits the electron and completely changes its properties. It changes its position, it changes its momentum, it changes its orientation in space, because the laser has energy. It has tons of energy relative to the electron. So if I then do a second experiment with the electron then hitting this film, I get a different outcome because I've changed it from the first experiment. So the uncertainty principle says that if you do an experiment, you basically trash everything you know about the electron after that point. And if you measure a second property of the electron, you're going to get uncertainty based on what you did to it in the first place. So learning two things about a small object like an electron is functionally impossible to a high degree of precision. And so that's written as a formula that looks kind of like this. Where is my formula? There it is. We'll go back to that previous slide in a second. So if I'm measuring position, like where is my electron, and then I do an experiment to measure how fast it's going, I can't do that. So I cannot learn both where my electron is and how fast it's going. I can only learn one or the other, because if I'm going to say, okay, at this moment my electron is moving 500,000 meters per second. In order to do that, I have to strike it with some sort of information. Typically, that's going to be light, right? And if I do that, now my electron is going at a different velocity, in a different direction. I've learned how fast it's going, but now when I try and detect where it was, it's no longer there. We have changed the nature of the electron by imparting extra information into it. So when I do the second experiment to figure out where exactly it is, it's no longer in that spot. And now it's going at a different velocity because I've already interfered with it. So I can't learn both of those things at once. There is too much uncertainty generated by me measuring the first thing to understand what the second one is. So that's where the uncertainty principle's name comes from. Now, mathematically speaking, this is the relationship between position and velocity. The product of the error in the position measurement and the error in the momentum measurement cannot be less than h over 4 pi. Which, again, we're not going to care about that mathematically. But the whole point of the Heisenberg uncertainty principle is you can never measure two properties at once. Because the first measurement you make may have a high degree of precision, but the energy that you impart into your object will change it so that you can't measure the second property with any degree of precision at all. Now, that's really unfortunate for us, because if we could know where an electron was and its momentum at any given time to a high degree of precision, we could solve a lot of problems. But this is just one of the fundamental problems of quantum mechanics, is everything is really frickin' tiny. And the objects that we have to actually measure tiny things are on the size of those objects. It's like measuring how tall people are, but you don't have centimeters. All you have are other people to measure by. You're going to get a lot of error because people aren't a well-defined thing, right? All right. So that's the uncertainty principle. The takeaway from the uncertainty principle is that if I'm trying to figure out where an electron lives at any given time, I cannot say that it follows an orbit around the nucleus like this. This is no good. Instead, what we do is we define a region in space, and we say that with 99% certainty, my electron is somewhere in there. And so this is where the uncertainty principle is going to have to make things a little bit more complicated for us. We can never draw our model of an electron as this sort of situation around a nucleus. So this is not something that we can do. Instead, what we're going to do is we're going to say, okay, here's the nucleus. I'm going to just draw this dotted line. And say, my electron is somewhere in this cloud, and I am 99% certain of that. Where is it the rest of the 1% of the time? It could be on the moon, it could be in the ocean, it could be taking a day off, it could be on holiday, that's fine. But 99% of the time, at any given moment, it's going to be in this cloud. And that's all we know. That's all we can say about it. With certainty. So we're going to call this electron cloud, we're going to call it this. We're going to call this an orbital. An orbital is the quantum mechanical probability distribution of where an electron will be virtually all of the time. Not 100% of the time, but nearly all of the time. Orbitals are the result of a wave function. Electrons behave like waves. We can calculate where the electrons will be based on that wave function. We're not going to show the wave function because we're done with math now. We're just going to output the shape of the wave function on the following slides. So to summarize everything that we've talked about for all of these quantum mechanical experiments is that electrons have a principal quantum number. That will be n. N will equal 1, 2, 3, 4, 5, etc. That is going to affect its ability to be a wave and how much energy it has. And that wave can be constructed into a shape which we are calling an orbital. And the orbital tells us with high probability where is our electron in space. That is all we get. We do not get to know exactly where the electron is. We only get to know it is probably in this region. And this region has this shape based on n equals 1, 2, 3, 4, 5, etc. I know that's going to be confusing. It's a very weird thing to get your brain wrapped around. Because what we're all going to want to do is we're all going to want to think of electrons as like, oh, it's like planets orbiting the sun. And the answer is, well, it would be if there was only one electron. With a ton of electrons and stuff, no, it doesn't work like that. We just have no idea where the electrons are if we can plot out their trajectory. All right, so there is our term, atomic orbital. Orbitals are regions of space that are defined by the likelihood of the electrons being there. An orbital is a three-dimensional representation. An orbit is a two-dimensional representation. So we are not using orbits. We are using orbitals. And we have assigned one quantum number so far to orbitals. That number was the principal quantum number n. However, there are many other quantum numbers. We're going to explore these other three quantum numbers that we are going to use to help us define with more exacting detail where our electrons are around the nucleus of the atom. N is more or less going to tell us the distance away. But L, M sub L, and M sub S do different things. And we're going to talk about those things one at a time. The first one, which again, principal quantum number, this is N. N correlates to energy. And energy correlates to distance from the nucleus. Now, these don't correlate exactly. They are not exactly the same thing. So we're going to see later on that something that has a higher energy might actually be closer to the nucleus in some special cases. But for the most part, this relationship will hold true. N equals 1 is going to be less than N equals 2, which is going to be less than N equals 3, and so on and so forth. As you increase in N, you get further and further away from the nucleus, and you get higher and higher and higher in potential energy. Now, other terminology that's going to come about for this is you're going to hear either your textbook or even me refer to this as the shell number. So the shell number relates to shells of electrons that surround a nucleus. So elements that have electrons in the first layer would be shell number 1, and then there's a second shell of electrons in the third and fourth, and so on and so forth. That's going to become more apparent later on what we mean by shells. But just keep the term shell in mind, because later on we're going to also introduce sublevels and subshells and stuff like that. So again, for principal quantum number, you might hear people say N, shell number. You might also hear level. These are all terms for just what energy level is our electron at. Now, the next few quantum numbers measure different properties of electrons. So the first of those that we're going to talk about is angular momentum. So all objects have angular momentum. Now, depending on how much they have, they're gonna have different trajectories in space as they wander all around the outskirts of the nucleus. The end result is that this quantum mechanical number will tell you what the shape of the orbital is. There are simple shapes, and then there are more complex shapes. And those shapes increase in complexity as the angular momentum quantum number increases. Now, there are only specific values of L allowed, and they are dependent upon the principal quantum number n. So, for instance, if n equals 3, then L, the angular momentum quantum number, could be 0, 1, or 2. Because the range of values for L is going to be, so the minimum is 0, and the maximum is n minus 1, and they must be integers. So if n was, let's say, 13, then this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are all possible values of L. All right. Now, an unfortunate side effect of this is that sorry, not of this, but of my font, is that L, so these are all L's. I'm going to write over all my L's here. There's an L right there. So only value. It looks a lot like the number 1. The kerning, not the kerning, but the serifs on my 1 are a little different than the L's. Please just be very careful. If you were unclear, like, is that a 1 or an L? Please ask. All right. So what I want you to do is in the chat, I want you to tell me what values of L are allowed for principal quantum number n equals 5. Now, while you're typing that out, what do these values of L mean? These are just states of angular momentum that the object we're looking at is allowed to have. So it could have state 0, 1, 2, 3, or 4. Now, in this class, we're not actually going to talk about what those states are in terms of math, but we're going to show them in terms of shapes later on. All right, you said 0 through 4, and that's correct. Very good. All right. Now, these shapes are actually going to correlate to letters. I know, this is getting really stupid, isn't it? If L is 0, we're going to call that an s orbital. If L is 1, we're going to call that a p orbital. L is 2, that's a d orbital. L is 3 equals an f orbital, and so on and so forth. We're going to see these terms come up again very shortly. Now, you can go past L equals 3. L equals 4 is actually a g orbital. L equals 5 is an h orbital. But as we're going to learn, no element actually has an electron in a g orbital, nor does there an h orbital, or further past that. All right. So those are the first two quantum numbers. We have learned that n could be any integer from 1 to infinity. L can be any value from 0 to n minus 1. And then we have this quantum number, m sub L. M sub L physically represents the magnetic component of the electron. Now, due to how magnetism works with, how do I want to explain this? So, due to how electromagnetism works, we end up with a lot of things that are orthogonal to each other so that they can exist without interfering. And basically, the summary of what the magnetic quantum number does is it's what orientation in space is the orbital taking. And so there are a bunch of different orientations that are possible, but they are all based on what angular momentum we have. In other words, what shape we have. So the values of M sub L, I got to draw over these again, will range between negative L to L. And these are all integers. In other words, we're just tacking on another rule here. So if we did something like this, so if n equals 2, then that means that L could be 0 or 1. And if L equals 0, M sub L could be negative 0 to 0, which is just that. Or if L was 1, M sub L would be negative 1 to positive 1. So that would include 0 in there. So in other words, what we are making is a series of nested rules. The first rule is choose an integer between 1 and infinity. The second rule is choose another integer between 0 and the integer you chose previously minus 1. And then so on and so forth. Why are we making all these stupid rules? And the answer is that this is actually going to model something very important to us, which we're going to discuss next week. We're going to get to that later. All right. So as an example, let's suppose that I had n equals 4. And of those possible L values here, one of them is 3. So for L equals 3, what is M sub L potentially? What are the values of M sub L for L equals 3? Type them out in the chat. Oh, look, nobody wants to write out all the numbers. You're going to have to do this on the exam, but I'll do it here. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. But there you go. That's the answer I'm looking for, is all 7 of those. All right. The rules are stupid and don't make intuitive sense because we are hand-waving all of the calculus that is used to get these. So what our task is going to be is to just remember what the rules are for calculating N, L, and M sub L. And I got to go back to my job of writing L's everywhere. So L, 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 L. What I really need to do is just use a different font for this. All right. Those are our 3 rules. There is an M sub S. We're not going to worry about M sub S just yet. All right. Now, I want you to write out all of the different possibilities for this, or for this principal quantum number. So n equals 4. So what that means is that write out all the possible L's, and then for each L, write out all the possible M sub L's. And I'll give you a hint. At the end, when you get to this step, you should have 16 of these. Now, you're not going to write those in the chat. You're not going to write 16 different lines. But what I want you to do is start with n equals 4. Okay, what are all the possible L's? Okay, we'll start with L equals 0. What are all the possible M sub L's for that? Okay, go to the next L. What are all its possible M sub L's? And so on and so forth. Do that until you've got them all. And what I want you to do is at the bottom of it, when you're done, type in the chat that you're done. And then I'm going to write them all out, and we're going to see if we could find anything interesting about this. Because it turns out that there's quite a bit going on here. All right, let's write all these out. So let's go over here, because I have more space on this. All right. How many different orbitals are there? So let's do this. N equals 4. So what are the different values of L for n equals 4? So I got L equals 0, L equals 1, L equals 2, and L equals 3. For L equals 0, the possible values of M sub L are just 0. For L equals 1, we've got -1, 0, and 1. For L equals 2, we've got -2, -1, 0, 1, and 2. And for L equals 3, we've got -3, -2, -1, 0, 1, 2, and 3. All right. How many total orbitals did I get? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So for n equals 4, I can describe 16 different ways in which electrons could exist at this energy level. And you'll notice that this number and this number are related. Keep this one in your back pocket. It will help you. For a given n, there are n squared orbitals. And that's just how numbers work. Then you'll remember that we assigned letters to each of these, didn't we? So how many different ways are there to create an s orbital? Well, there's only one. So there will only be one orientation of the 4s orbital. What about the p orbitals? There are 3 of them. How many d orbitals are there? Well, there are 5 of those. Oops, I wrote the wrong thing. 5, 4 d orbitals. And then there are that many 4f orbitals. Now, interestingly, let's suppose that I did this. If I did this, n equals 3, what all changes here? The only thing that changes is that L can only be up to 2, and then all of these would change right here. But everything else would be the same. So this number right here that I'm sticking in front of my letter, this is just n. So I could have a 1s orbital or a 2s orbital or a 3s orbital or whatever. But what I can't have is I cannot have a 3f orbital. And the reason for that is because for n equals 3, L cannot be 3. So only certain types of orbitals are going to be available based on what principal quantum number we are looking at. So as n gets bigger, more L's become possible, and thus we can have more different types of orbitals. I don't know why everybody is messaging me in my other class, but I need to turn this off so I can't hear them. There we go. So just by writing out all the different possible orbitals and their names, we've actually learned a lot about structure. So you could see that this is starting to do like a 1, 3, 5, 7 thing. If I had L equals 4, there would be 9 for a total of 25, which checks out because 5 squared would be 25, and so on and so forth. So there's definitely some math hiding behind the scenes here, right? There's a logical order to all of this. It's just, what the heck is that order? All right. So I think I have one more here. Yeah, there we go. So I've sort of already done this for n equals 3 by showing you over here where all you do is scribble out the L equals 3 row for n equals 3. That's not what I meant to click, sorry. So I want you to write out all of the orbitals and, oh, you know what we should do? Hold on. We didn't actually assign them quantum numbers, so let's do this real quick. Okay. So if I want to assign quantum numbers to my orbitals, here's what you do. This is a notation that I believe your textbook uses, but I also just have opted to do this. The quantum numbers that we're showing here are going to be like an address for an orbital. So the way that you do this is you just report n, L, m sub L. So, for example, if I wanted to look specifically at this orbital right here, I would say, okay, what's its n value? What's its L value? What's its m sub L value? And so I would say, okay, that was n equals 3, L equals 1, m sub L equals 1. And I could write this for any combination of n, L, and m sub L that I wanted to. However, these all have to follow the quantum mechanics rules. So what that means is that for some quantum numbers, I will get an invalid result if I do, like, say, this. What's wrong with this? Well, this one, L can only be 0 to n minus 1, right? 3 is not the same. 3 is too big. So if I have 3 here, and n was 3, the highest I could do is 2. So this is no good. So this would be an invalid quantum address. This would not represent an orbital that exists. So in this next question right here, when it says which of the following quantum number sets is invalid, that's what I'm saying is which of these breaks the rules. Because one of those has quantum numbers that I cannot actually correlate to a real thing. So that's what I want you to do. So tell me which of the sets of quantum numbers is invalid. We'll go over the answer to why that is. And then we're done for the day because we're out of time. All right, one more minute. We'll go over the answers. All right, so we already did the n equals 3 on this previous slide, so you could see that again here. Oh, well, if I scroll it up, you could see that. So there's n equals 3, which would just be L equals 0, L equals 1, L equals 2. All right, so you pause the video for that. Let's find which one of these is invalid. So for n equals 3, L could be 0, 1, or 2, so this is valid. For L equals 0, M sub L could be 0. That one works. For n equals 2, L could be 0, 1, or 2. Sorry, 0 or 1, not 2 would not work. But for L equals 1, M sub L could be -1, 0, or 1. So that's good. For n equals 1, L can only be 0, and for L equals 0, M sub L can only be 0. So that one checks out. But here's our issue. So for n equals 4, L can be 1. That's valid. L could be 0, 1, 2, or 3. But for L equals 1, M sub L can only be -1, 0, or +1, which this is not one of those numbers. So that set of quantum numbers does not represent something that exists and would not be an electronic address. All right. So we're going to take all of the structure that we've learned for organizing our orbitals, and what we're going to do is eventually we're going to convert this into like a pictorial diagram. I'm trying to find a slide that has an example of this on here. Yeah, here we go. This is what this looks like. So you're going to see this structure take place as like a diagram where we can put electrons in here. So here would be n equals 1, L equals 0. Here's n equals 2, L equals 0. N equals 2, L equals 1. And then here are each of the M sub L's in here, and so on and so forth. So then this light blue would be, here's n equals 3, L equals 0, L equals 1, L equals 2, and so on and so forth. So all of this number crunching that we are doing with all these rules that, like, it seems like it makes absolutely no sense what we're doing with it right now. There is absolutely a method to this madness, and it's going to take us a week or so to get there. So tune in next week, but for now, don't worry about it because you have an exam tomorrow, and this is not on that exam. So instead, I'm going to sneeze. That's what I'm going to do. Sorry, I had to mute myself there. Instead, make sure you are preparing for the exam, which opens tomorrow. Last call for lab number 2 is tonight. If you want your exam moved to Saturday because you need an extra day to study, please get in contact with me by 11:59 p.m. tonight. I will check timestamps. And if you've emailed me before that, whether or not I have emailed you back, I will grant your request. If you email me back after, or if you email me after midnight, I will tell you, please take the exam today. The exam is... You know, that's a good question. I don't actually know. What do I have the exam set to? Let's see. Sorry, I'm looking it up right now. Midterm exam. I gotta click over here. Time limit I have set to 95 minutes. You get 95 minutes. Which is more than enough time to do it. I do not expect that you'll need that long. Alright, yeah, that's all I have. I'm going to hit this button that starts this music, which means it's time for me to go. Again, last call for lab worksheet tonight. Exam number 1 tomorrow. Email me if you want it moved to Saturday. Take care. Good luck. We're all counting on you.